Hello everyone and welcome back to physics class. Today we are going to be looking at velocity as a function of time. In other words, velocity time graphs. So you might be wondering, what is a velocity time graph? Well, on our x-axis we have our value of time. And then on our y-axis we have our value of velocity. This is different from the last graph that we looked at. Here, we are comparing how fast our object is going compared to the time that's elapsing. Now, when we read a velocity time graph, we can read three different types of things that are happening, different situations, I should say. So the first one here, we have this section up here, which is increasing up. So this means that we have a change in velocity. And this change, because it's increasing, is positive. If we were to take a look at this flat line right here, this is flat on a velocity time graph, meaning that this is constant velocity. Finally, if we look at this section right here, this decreasing one, we also have a change in velocity here. But because we are decreasing, it's a negative change in velocity. Let's take a look at an example. Here we have a graph, and we have velocity in terms of meters per minute, and we have time on the x-axis in terms of minutes. First question we want to consider is, where do we have constant velocity? Now, remember, constant velocity is our flat part right here. This is the only part that we have constant velocity. We don't just want you to show us on the graph. We also want you to indicate on the time interval. So if we start here and we find that we start at t is equal to 10 seconds, and then it's constant until we hit, it kind of looks like 16 seconds, so t is equal to 16 seconds. So this is the time interval for our constant velocity. Now, what about our changing velocity? Where do we have changing velocity? Well, we have a couple. We have this one right here, this section here. And then we have this one here, this long one, and then we have this other one down here. So I'm going to label the sections here. So this is section 1, and then this one here is section 2, and then this one here will be section 3. So for section 1, it starts at t is equal to 0, and it goes until, oh, I just realized that my units are all off. It should be minutes. Oh well. And it goes until 10 minutes. Let me change those. So that's section 1. Section 2, it starts at t is approximately 16 minutes. And it goes until down here, which is 40 minutes. T is equal to 40 minutes. Finally, the third section starts at t is equal to 40 minutes, and it goes until t is equal to 60 minutes. Not only can you tell on a velocity time graph the time intervals where you would have constant or changing velocity, but you can also calculate our displacement from a velocity time graph. Remember, displacement is our change in position. The way that we calculate displacement is that we consider the area between the curve and the x-axis. So in this case, it would be, we consider this area right in here. Now, we could find the area of this shape. It's a trapezoid. We could find that area. But I like to break it up into different shapes, simpler ones, like this one here. We have a triangle here where, let's say it's like this. So this is my first area right in here. And then we have this rectangle here. Oops, I wanted it to be blue. To be right here. So we're going to want to review some very important formulas that we need to remember when we calculate displacement from a VT time from a velocity time graph. The first one is the area of a triangle, and that is your base times your height divided by 2. Last is the area of a rectangle or a square, either way. It's vistas. The area of a rectangle is your length times your width. So these are some very important formulas that we need to remember. Let's take a look at an example. Here we have some kind of object moving at a constant velocity, and then it suddenly starts to change its velocity in the negative direction. And then here we can see that it's still changing in the negative direction. It's just a less steep angle. So let's break it up into 3 sections. We have this rectangle here that I'm going to call section 1. We have this triangle in here, which I'm going to call section 2. And then we have a triangle right here. We always have to go between the curve and the x-axis. So I'm going to call this section 3. So let's go ahead and calculate my area for section 1. So this is a rectangle. I'm going to take my length times my width. My length is 6. 6 times my width, which is 15. So if I were to do 6 times 15, I would get 90 meters. Area 2, we need to take our base, which in this case is 10 minus 6, which is 4, times our height, which is 15. Divide that by 2. So 4 times 15, divide that by 2, gives me 30 meters. And then lastly, I have another triangle. So I'm taking my base again. So this is actually 14 minus 10. So that's 4. And my height this time is negative 10. Negative 10 divided by 2. So then I have 4 times negative 10 divided by 2 is negative 20 meters. So this is the displacement for each and every single section. But what if I was asking for the total displacement? Well, if I was asking for total displacement, then I would simply take all of these numbers and add them up. So 90 plus 30 and plus negative 20, and I would get, so 90 plus 30 minus 20 gives me 100 meters. That is the total displacement of this object. And that is how you find your displacement from a velocity time graph. Now remember, it has to be a velocity time graph. You don't want to use this on any other kind of graph because it's not going to give you the same information. It has to be velocity and it has to be time. So, thank you for listening, and I will see you next time with a whole brand new topic where we start talking about acceleration.